So ultimately, we're going to start using your knowledge of transformations. It's the best way to think about graphing whatever you're dealing with because it applies to everything we do. But we need to start with a basic form. Same way when we did sine and cosine, we started with those graphs and then we built up. So let's just take a look at the basic form for a couple exponential graphs, and then we'll learn to move them around. So for the first one, I've got 2 to the x. So for example, if I stick in x equals 1, it's going to have a value of 2. Which on my scale is quite low down there. At 0, it would be 1, so again, it's quite low. At 2, that's 2 squared is 4. At 3, it'll be 8. Sorry, 4 should be higher than that. 4 is probably here. So at 8, probably be something like that. Then at 4, it would be 16. So let's say probably about there. So that's probably enough points that you'll see a decent shape of the curve. It's going to go kind of like this. So there's our basic exponential graph. And we'll talk about some of the features in a sec. There's nothing wrong, by the way, if you're, stumped for trying to figure them out, to just go back to the basics of graphing and make an XY table, like x equals 0, y equals 1, x equals 1, something like this, right? That'll get you some points. That'll help you see the basic shape before you do transformations. Okay, in this one, it's going to be a little bit different. So it's a little harder to think about what this picture is going to look like unless we pick some strategic points to talk about here. So we'll start with a simple one. X equals 0, I'm going to be at, nice, it's not even 9 o'clock in the morning yet, and you guys are, that's impressive for teenagers, by the way. Impressive for a lot of people, but especially teenagers. Let's try x equals 1. Then where are we at? 1/2, that's right. 1/2 is the exponent is 1, so it's going to be down here. Let's do one more on this side. So if I square it, what am I going to end up with? Sorry? Yeah, 1/4. Okay, so it's kind of hard to tell what's going to be happening with this graph because it's so small. So let's go the other way. Let's put in -1. What's going to happen if I put in -1 for x? That's, yeah, so it's going to be 1/2 to the -1, which is 2. Remember, you flip the exponent when it's negative, so this is going to be 2. What about at -2? Yeah. Let's go one more here. -3. Yeah, it'll be 8. So I'll plot those so you can see them. That'll be 2, then 4, and 8. The next one would be 16, so just so I know I have a good graph. Okay. Okay. So there's the two graphs. Now I'm going to say that we really only need to think about one type of graph, which is going to be the one on the right-hand side. Because if you're clever about this graph, you can tell me with transformations, you could predict what's happened. So look at it visually. What do you think has happened visually? And use transformations thinking about it. So look at the graph on the left. Look at the graph on the right. Can you describe the one on the right with transformations? The one you started with is on the left. Yeah, a y-axis reflection. So y-axis reflection, why would that be? Well, this is the same thing as 2 to the -1, right? 1/2, I could write it that way, which is the same thing if you use your exponent laws as 2 to the -x, right? So that means I really don't have to worry about all the fractions and other things. My base graph is just going to be the one on the left, and today we'll practice, finding and using transformations on them. So for exponential graphs, our domain is all real numbers. And of course we have a nice abbreviation for that. We can just use capital R. I think your textbook uses a scripty fancy R. Generally it's like a double bar or whatever. I'll know what you mean if you use a capital R. What's the range of these graphs? Yeah, so we would just say greater than 0 here. So the range is y great. Oops, that was clever. Y has to be greater than 0. Does it ever touch 0? Yeah, that's the tricky part, is if you think about it, no matter how big of a negative you get, there's still a number on the bottom. It might be like 1 divided by 100 trillion, but that's still not 0. No matter how big the bottom of your fraction gets, it's still not 0. So it's just greater than. And we have an asymptote. What's the asymptote? It's kind of like a fence, right? A place the graph can't go through. So do you see one on this picture? Yeah, the x-axis. So if it might be harder for you to see, let me use a thicker pen. This is okay, so here's the asymptote that we were just talking about, and that happens at y equals to 0. So just a quick review of your transformations. These were the pieces we talked about, and we'll just label them to remind you. Your vertical, hitting that space bar this morning, sorry. Your vertical stretch factor is this one. Your horizontal stretch factor is this one. Horizontal translations happen on that one, and vertical happen on this one. So like when we did trig, we're going to be talking about just exponential. So we're going to have a quick way of looking at the exponential graph. So here's what it would look like if we're working on the exponential graph. If I put in a, b, h, and k. It's not really necessary that you think about it this way, but some of you might find it useful to remember that shortcut. But here's where the pieces fit in if we're talking specifically about an exponential graph. Vertical stretch factor is there. Horizontal stretch factor. Horizontal translations are there. And then vertical is this piece. Okay, so let's use your transformations knowledge then so that we can come up with a graph fairly quickly. So this is the one we're interested in, this graph, but we're going to go transformation style. So what's the base graph here? If we took away all the transformations, can anybody tell me what's the simplest, the form that just gives me a base graph? Yeah, 2 to the x. You get rid of all the other pieces there, and we're just dealing with 2 to the x. So if I really wanted to work this through with transformations, I can just go with a nice simple, pick some key points. If we know the basic shape, 3 or 4 points is going to get us enough information to graph this. So let's pick a few points. Let's try like, maybe -1, 0, 1, 2. And remember, right now, I'm forgetting that I have this monster graph. I'm just going to think about what's the base graph, the simplest one. Where are those points? So this is going to be at a half. It's going to be at 1, 2, 4. And just like we did in transformations, we're going to apply the list of transformations to each of these points in order to come up with the transformation. So I have these 4 things that I'm going to deal with. So maybe we should put them in the margin here. So, oops, sorry, I forgot reflections. reflections. Is there a reflection in this graph? Which one does it reflect on? Y-axis, good. Is there a vertical stretch factor? What does it do to the graph? Yeah, so it's going to be a quarter. Multiplies by a quarter. Horizontal stretch factor? Yeah, it's 2. It was a half here. Now it's going to be 2. And what about left and right? What do we do left and right? Left 1, down 3. Yeah, so I'll just put left 1, down 3. So if I take my points here and I move them through reflections, let's start with the point -1 and 1/2. That point is going to become 1, 1/2. 0, 1 will stay 0, 1. 1, 2 will be -1, 2. And 2, 4 will be -2, 4. So that's my points after the reflection's been done. Now we'll apply our expansions and compressions. So the vertical one is going to be by a quarter. The horizontal one by 2. So horizontal by 2. That's going to make this an 8, 1/8. This will be, what do we have here? 0 and 1/4. Then I'm going to have -2 and times it by a quarter gives me a half. And this one here is going to be -4 and 1. And let's see here. This time we'll do translations, moving them left 1 and down 3. Okay, so left 1 puts this one at 1. And if I go down 3, taking 3 away, that's, well, might be useful to think about it like this. Because we don't really, if I'm going to graph it, I'm moving 3 units down. You could put in the decimal number there, but anyways, I'll show you 1/4 minus 3. And this one's going to be -1, 1/2 minus 3. And I'm running out of space here, but hopefully it'll fit. -5. Oh, sorry, that should have been a -3. -5, and if I go down 3, it should be -2. So here's my final set of points on this graph. I'll put those on the picture like we had before. So at x equals 1, it's going to be 1/8, and then I got to drop down by 3. So it's going to be, it's hard to see on the picture, but it's going to be something like this. 3 down. Then it's going to be at, the next point I had was -1, and 1/4 minus 3. So it'll be a little bit higher, but more or less in the same spot. At -3, it's going to be 1/2 and then 3 down. So again, got these fractional spots, but something like that. And -5, -2, that's going to be like, here. So that's a really unfortunate, but it seems like I picked a bad. I should have had more. I should have had more of the graph going this way in the picture, because if I did, then it would start to. Oops. We'd get a curve that started happening over here, but we sort of ran out of space. So my apologies. I'll have to correct that graph. Just a poor choice of domain and range on that picture. But if I look at it this time, the domain this is the most boring question for an exponential graph. It's always all real numbers. There's no number you can't put into the exponential graph. You're going to get all real numbers out of it. The range, however, in this one, it's going to be the asymptote we're going to deal with, because we dropped it down 3, that means the asymptote is going to be -3. And this graph is rising, so you see the graph starts going up, which means we're going to be everywhere greater than that asymptote, everywhere above -3. So try using your transformations knowledge to graph this one and see what you come up with. So I'll just try and catch up to you. The base graph here should be 1/2 to the x. Okay, so you have an x-axis reflection, so your y-coordinates are going to become negative. Then you have a vertical stretch of 4, and nothing happens horizontally, so question? Oh, sorry, let me... and then I have -16 here, -8, that'll become a -2. And then I just have to do my translations, which is going to push this graph 40 up and 3 to the right. So that'll be 0 and 8. +1 and 24. And let's see here, that'll be +2 and 32. Then 3 and 36. And this is going to become 4 and 38. Okay, so if I started with my points this time at 0 and 8, that's about there. 1 and 24, I'm going to guess that's, let's see here, that's 25. So 24 should be just underneath that. 2 and 32, so that's 30. So somewhere like that. And 3 and 36, something like 35 is that line, so it's probably a little lower. And then 4 and 38, probably going to look like that. So this graph, if I connect the dots, would go this way. So the most boring question, the domain is all real numbers. The asymptote, do you see where the asymptote is on this graph? Yeah, it's at 40 this time. So if I kept going further, I'd be able to see that asymptote there, which would be at y equals 40. And once you know where the asymptote is, you can ask yourself, does this graph go above or below it? It can't go through it, because it's an asymptote. It goes above it or below it. In this case, it's underneath it, so everybody is going to be less than 40. Okay? So let's talk about some quick ways of predicting this kind of stuff from the graph. the asymptote and the range, because the domain is always going to be all real numbers for the ones that we encounter. So let's see if we had an equation like this one. Okay. Can you look at that and tell me where the asymptote would be?
7.
Yeah, good. It's going to be at 7. So those of you who are catching on to this pattern, why do you think that is?
Because it's equal to y.
Well, let's use our transformation. So those of you who aren't quite there yet, where's the asymptote normally when you have an exponential graph? Don't transform it. Where's the asymptote going to be? 0. What happened to this graph? Up by 7. So that means that's why we have an asymptote at 7 now, is it got shifted up by 7. Okay? Does this graph go above the asymptote or below the asymptote? It goes above. Normally, the exponential graph goes above the asymptote, right? What's the only thing that's going to make it go below? Right? Normally it does this. What's the only thing that's going to make it go like that? A reflection. What kind? The x-axis will mess it up. So if there's a negative sign in front here, that tells you it's going to flip down. It's going to be below the asymptote. So try and make the prediction on the next two equations without having to graph it. Where would you find the asymptote and where would you find the range? Okay, so if you had a minute to think about it, this should be a pretty simple question for you now. Where's the asymptote going to be on this graph? Good. Does this graph go above or below the asymptote? Below, so it's going to be y less than -2. Sorry, and I should have put it here, y greater than 7. Okay, so if you've already had a chance to call out, let your neighbors think about it a bit more. I'm going to look for some new people to help share out. Where's the asymptote on this one going to be? Okay, and is it going up or down? So what should the range be? Less than -3. Good. Okay, so that's one thing then that you won't, if that's the thing you're faced with, where's the asymptote, what's the range? You don't need a full graph. Unless you're specifically asked for the graph, you don't need to do that, okay? But we also want to be able to then think about how do we get an equation from the graph? And we're going to use what we just thought about with asymptote and range to help us figure this equation out. Okay? So if this was our picture, how could we reconstruct the graph that it came from? Well, one thing you always want is good points, right? So for example, when I look at this, I can see a really nice point to use right there. Like, you could use this one. There's nothing wrong with that. But it's hard to tell what the y-coordinate is, right? So let's not. Let's just use good points. Can anybody else think of another good point? Maybe you can give me the x-coordinate, and then I can highlight it. What x-coordinate will give you a good point to work with on this graph? Yeah, at 3, there's a nice point there. There's more here, like at 4, there's a nice point there too. So I'll label them here so that way you can see. This is 2 and I believe 3. And this is 3 and 7. And this one here is 4 and so 15, 16, 17, 18, 19. Okay, so here's the monster that we have to tame. Sorry, I believe, yeah, I believe this was the one that, not that it matters, but I believe this is what we were using before. So to figure out what the equation is, I have to be able to stick all of those things in. One of those letters you should be able to tell me just looking at that picture. What do you think? If you just looked at that picture, you didn't even look at the points, one of those you should be able to tell me. What's the value for k? 1, good. It's the asymptote right here. And what is it in this case? Oh yeah, we already said 1, right? Sorry. Don't worry, I'll be awake soon. Okay, so now we got 3 more letters to tame. All right. What else do you think we could come up with here? Okay then, not such an easy question the first time you see it, right? But let's think about when we reconstructed this graph. Okay, this time I went over 1 and up 4. the next time I went over 1 up 12. So what did I multiply there in order to get that much higher up? Yeah, so I had to triple what I did before. If you were to make a prediction for me, where do you think the next point on this graph would be? It'd be 36 higher than 19, right? So if we keep multiplying by 3, what does that kind of tell you about this graph? Hold on, hold on. Think about it in terms of exponents. If you're multiplying by 3, what's the, use some math terminology, 3 is the base. It's the base, right? Because you keep multiplying by 3 every time you move over. It's triple what it was before. So C is equal to 3 in this picture. Okay. Okay. A and so the nice thing is now that we know what the base is, we know what our base graph was. Okay. So I'm going to show you what some points would look like on that base graph to help you think about what's changed. So normally it would have been like this. Well, it won't fit on after that, so I'll just do my best estimate. And I'll label those points for you. So the purple is what our base graph would have looked like. It'll help us think about how it's changed. At 2 it would have been 9 because I'm squaring 3. Okay. So we know it's been moved up 1. What else has happened to this graph? Okay, well one hint I'll give you that you might want to consider working on. One of the points that we're going to look at is 0, 1, right? Because 0, 1 in the original graph, 0 is nice, it makes x disappear, right? So what I want you to think about is where would that point show up in the new graph? Because what happens if we stick in x equals 0, then that's one less letter that we have to think about in this problem. Okay, so here's a slight, we'll just say if we knew we added 1, here's a bit of a hint. This would be 2, 2 then. This would be 3, 6, and this would be 4, 18. Because we added 1 in the transformed graph. So if we subtract 1, that's where we're going to end up is 2, 2, and 3, 6, 4, 8. We're trying to work backwards to where we started. So Stacy was actually able to find the whole graph starting at that point. So I'm going to give you just another minute to see if you can work out how she did once you took the shift away of moving it up and down. Okay, maybe I'm making you work too hard on a Monday here. Let me show you. I was hoping that because of the Stacy's actually done it, but so I'm going to give her some credit there for figuring it out. But the reason I drew these stairs for you is I was hoping that you were going to draw those kind of stairs on your picture. I guess I should use purple just to make them. So my purple stairs, here they go up 2, then it goes up 6. And now, okay, the reason it's nice to think about it that way is it actually removes a bunch of the information in the problem. So it went up 2, then up 6. And what's it doing in the other graph? It went up 4 and up. Okay, so what's the difference? It's twice as much. So that means vertically, I've stretched it by 2. Okay, so now we have another value here. Okay, and you're not going to find that there is a horizontal stretch factor here. So all we need to think about then is, what's that shift that's happened? How have these points been moved on the graph? You can see which way has the graph moved, left or right. Remember, we started with the purple graph, got a black graph now, so we go left or right? Okay, we went right. And how much did we, do you think we would have done that? If you're not sure, we only have one thing left to find. So here's the way we can find our last piece of information. I'm going to stick in one of the points to my equation. 1 is equal to 2. Oops, sorry, that's the base graph. I'm going to stick in one of the points. So I'll use, say, this one here, which is the point 2, 3. So this will be 3 times 2. Whoops, and the value of x is a 2. So if I start to rearrange this, that'll be 2 is equal to 2 times 3, 2 minus h. 1 is equal to the 3 to the 2 minus h. So how on earth am I going to turn 3 to the something into a 1? What do I have to do to make this? Yeah, the exponent has to be 0 in order to get 1 out of it. So 2 minus h has to be a 0. H is equal to 2 for us, because that's going to give me 3 to the 0 equals 1. That's the exponent I'm looking for. Okay, so after all that, we have 2 times 3 to the x minus 2 plus 1. All right, so let's put that beast behind us. Aside from trig, the next, I'd say the next most applicable thing that you can get in our course is exponential and what you're going to find later, log graphs. Newton's law of cooling or heating works this way. So if you look at the temperature versus time of anything, it decays with an exponential graph. So we can model things like, you know, a cup of boiling water, or if you're cooking, or who knows, one day you're working at NASA and you need to know how hot the fuselage is going to be coming through the, I don't know, anyways. Probably not that practical. But here's a scenario. It says a cup of water is heated to 100 degrees Celsius, then allowed to cool to room temperature, which is 20 degrees Celsius. If we found out that it decreases by a quarter every 5 minutes, we want to first find an exponential graph and use it to predict the temperature in 15 minutes. Has anybody noticed that Starbucks has timers? So like they stick your coffee under the steamer, right? And it boils your coffee up very hot, and then they hit a timer because they're not going to serve it to you before when it's too hot, because they get sued when that happens, right? So somebody's figured out, okay, if your barista is heating it up to 95 degrees every time they make a coffee, it needs to sit for a minute and a half before it's safe to serve the customer. So watch next time you get a Starbucks, you'll see that it depends on what you ordered, right? But you'll see them hit a timer before they put it out. But anyways, here's a model we could use then. If we lose 25%, that means 75% remains after 5 minutes. Whatever you're modeling, it's not helpful to think about, well, sometimes I suppose it is, but more often than not, it's helpful to think of what's left, not what you lost. Because that's the quantity we're measuring now, is we want to know how much temperature we have, not how much temperature we lost. So 75% of the temperature remains. So if I wanted to show you what that would look like, here's a model for it. We started at 100 degrees Celsius, and 75%, I'll write it as a decimal, 0.75, and let's put an x here, where x is 5-minute intervals. So if we wanted to predict after 15 minutes, how many 5-minute intervals is that? Good. Okay, this is easy after that exponential graph, right? It's 3 5-minute intervals. So we would stick in a 3 for x. Or we can come up with a better model. Where we just say it's x over 5. You give me the number of minutes, I divide it by 5. That tells me how many 5-minute intervals have passed. So if you give me an odd number like 18 divided by 5, the decimal will be already calculated in there when you put in your calculator. Okay, so let's work out here what we get for 15 minutes. Okay, so it should be 42.2 degrees, and I promise one day you can try to earn some hot chocolate from me in calculus. We'll actually derive how Newton got this formula, and then we'll actually test his theory out in practice. We'll boil some water, and then we'll try to come up with a model to predict when I can safely give it to you. Okay, so here's another scenario where you might encounter an application for exponential decay. The half-life of, I think this is americonium or something. I'm not the chemistry buff, so it's 432 years. If a smoke detector has 200 micrograms of it, let's create a model to show how much is left at any given time. Okay, so we'll stop there before we look at the rest of this problem. But okay, half-life is every 432 years. And I start with 200 micrograms. So this is the simplest exponential model, but remember you have to tell yourself this is where x is in 432 year intervals. So you might say to yourself, hey, that's not super practical. How could we make it in terms of years?
X over 432.
Yep, x over 432. That'll tell me how many years have gone by. So that's my model, and it says if the smoke detector needs at least 180 micrograms, how long will it last? So this is what we're trying to figure out then, is if I give you, say that's the threshold where this smoke detector won't work anymore, and I don't know, by the way, if that's true, so don't take my word for it. If this, just test it. There's a little test button. Just push the test button. This is the equation we're trying to solve. Now the good news for you is we have graphing calculators, so let's put them to work. Okay, so the model that we had was 200 times the half-life to the, we said x over 432. And it was 180 that I'm looking for it to intersect, 180 micrograms. So let's think about the window here. If you want a good picture, it helps just to spend an extra minute. I need to see 180 because I need to see where the graph touches 180. So it's going to make sense if my window, if I use a y scale that goes from like, I don't know, let's say 170 to 190. Yeah, it's not going to show all of the graph, but all I need to see is where it hits 180. So I know 180 is going to be right in the middle of it. That should be a nice graph to look at. Now, how big do you think the x values should be? If you start with 200 and 432 years have gone by, how much is left? 100, half of it. So we don't need all 432 years. We can probably even do with less than that. I'm going to say it's probably a safe bet to say, let's try 200 years. You could go to 432, there's no harm in that, but you know this window should have what we need for the picture. So there's my decaying smoke detector, and there's 180. And remember, it goes second function, calculate, and we go down to the intersection, where you'll move the cursor along the curve. So let's try somewhere around here should work. I'll say yes, and I'll say yes, make my guess a little closer. Magic happens, and there's an intersection. So 65.67 years. Okay, so x equals 65.7 years.